In this lesson, we're going to examine a third type of discrete probability distribution we call the hypergeometric distribution. Before we get to that, though, let's take a look real quick at some of the things we looked at yesterday or last day, and we're looking at binomial things. So you have the option of two types of tests tomorrow. First is 30 multiple choice questions, each of which has 5 possible answers, or you can choose 50 true and false questions. But I'm not going to tell you what's on the test. You're going to have to guess, randomly guess at each of the answers. Which of these two tests would be better for you? Which would you expect to get higher on? I'm hoping you think about this as an expected value. Our expected value for the multiple choice test, there's 30 questions. The likelihood of getting any one question right is 1 of the 5 possible answers. On the true or false one, you have 50 questions, a lot more of them, but the likelihood of each one right is being 1/2, just randomly guessing. So if we calculate this, you should expect to get 6 right answers in the multiple choice, but 25 right ones on the true or false question. So common sense says, which of these two should you get? Which one should you be likely to do better on? Well, this is 6 out of 30, or if you will, 20%. And this is 25 out of 50, or if you will, 50%. If you have to choose a test you want to guess at, pick the one that's got less options, because you have a better chance of being right, even though it's got way more questions. Okay, both of those things are considered binomial because they're repeated independent trials. Just because you get the first question right doesn't mean you have the next one right or the next one wrong. It's completely starting over again. Okay? But we can also have repetitive things that occur in dependent ways. Okay? So for example, let's say we're dealing cards from a deck. As we deal the cards, the probability of each successive card depends on what the previous one is. For example, let's say I have my 52 cards in my hand, and I deal a 10. Well, the chance of getting a 10 is 4 out of 52 the first time. But once that card is gone, the next card, being a 10, is only 3 out of 51. And once that card's gone, it's 2 out of 50. And then the last chance of getting a 10 is 1 out of 49. The probability is changing at each stage. When I'm doing the guessing at a test, it doesn't matter if I guessed right or wrong the first time, but it does matter when I'm dealing cards if I got something or not. Okay? These kind of situations are hypergeometric, where the probability distribution involves a series of dependent trials, again with success or failure. I got it or I didn't. Okay? These things involve combinations, since order doesn't matter. It doesn't matter which 10 I dealt first, the club, the spade, the diamond, the heart, just the fact that I did get a 10. I was successful. Okay? These things are things we've actually done before. We just didn't call it hypergeometric. We just called them combinations. So the first example here, a hat. It contains 20 names, 12 of which are female. 5 names are drawn from the hat. What is the probability that there are 2 female names drawn? So if I'm thinking about a distribution, x, px, I could write out no females, 1 female, 2 female, 3 female, 4 female, 5 female, and go through the whole distribution. Or, as we want in this case, I can just look at specific cases, 2 females. Okay. To do this, we're going to take the things we know how to do. I need to get females. Well, how many females are there? 12. So I need 2 of them. But we've talked in the past that this implies something. If we're selecting 5 names and 2 are female, it implies the rest are male. So I need to choose 3 males from the remaining 8 people. There's 8 because there's 20 to start and 12 were female. Out of, I want to, how many different ways I can do this? There's 20 people and I chose 5 names. And you may recall in the past, we always said these numbers should add up to that number, and these numbers should add up to that number. And this question is a hypergeometric distribution because the probabilities change. If the first name is female, it changes the probability of the next one being female, and the next one, and the next one. But it's exactly what we've done before. We just didn't call it hypergeometric. We just said, oh, we're doing probability with combinations. And there's our answer. To find the expected value for hypergeometric, determine the proportion of the total of the thing you want and multiply by the number of trials. In other words, n times p again, where p is proportion. That's all we're doing here. Okay, so what is the expected number of women chosen? Well, how many trials do we do? We take 5 names out. What is my proportion of women? Well, 12 of the names in there are women of the 20. So 5 times 12 out of 20 gives me 60 over 20, or 3. I should expect 3. Okay, let's try another one. A box contains 5 dozen heads of lettuce. There are 8 spoiled heads in the box. A person chooses a dozen heads at random. What's the probability to get none of the spoiled heads? So I know this is hypergeometric because I have a select group of things. Once I start taking things out of that box, my probability is going to change. If the first one is spoiled, there's one less spoiled head left. The next one's spoiled, there's one less spoiled. It's changing as you go. So I can do this idea of hypergeometric stuff, not binomial. I want to know the likelihood of getting no spoiled heads. How do I do that? Well, how many spoiled heads are there? There's 8. And I want no successes. How many non-spoiled heads are there? Well, 5 dozen heads of lettuce. There's 12 in a dozen, right? It gives us 60. There's 60 heads altogether. 8 of them are spoiled, which makes 52 that are not. And I want to get, we're selecting a dozen at random, 12 of them. Out of, there's 60 heads altogether, and we're taking a dozen. Into our calculator as we go, and we should get 0.1475. Okay, what's the probability to get at least one spoiled head? So I could go through and figure 1 spoiled head, 2 spoiled head, 3, 4, 5, 6, 7, 8, or we know it's faster if I want to do at least 1 to get rid of what I don't want. And the good news is we know the probability of 0, and we just did that one. Okay, so this is a quick one. 0.8525. I'm going to try another one. A fishbowl has 10 guppies and 8 goldfish. 4 of the fish are removed randomly. What's the probability that at least one of these is a guppy? Well, there's those words, at least one. Which we know we should get rid of what we don't want. Okay, let's find no guppies. There's 10 of them. I want to be successful no times, which means I want to fail 4 times. And I have to fail, it means I'm selecting goldfish. Out of 18 fish, I want 4 of them. Give it a try, and hopefully we get 0.9771. A pretty good chance you can get at least 1 guppy, which makes sense because we have more guppies than goldfish. It'd be unlikely to get all goldfish. And the fish bowl also contains 3 angelfish. How many angelfish would you expect to remove if you chose 5 at random? So I see the word expect, so I'm thinking expected value. My trials, I'm taking 5 fish out. My proportion of things that are angelfish is 3 out of, we had 18, 10 guppies and 8 goldfish, and we added 3 more angelfish in, so 3 out of 21. Which gives us 15 over 21, or, if you will, 0.71. You should expect less than 1 angelfish. Again, it makes sense because we don't have very many angelfish in there. There's only 3 of the 21. So even though we selected 5, odds are better that you should have more goldfish and guppies. Okay, last one. We can work backwards with this stuff. So, estimate the size of the seal population in a certain region of the Arctic. If in a hunt of 50 seals, 20 were tagged. And it's known that 1,000 seals have been tagged before the hunt. Well, the nice thing about hypergeometric things is proportions. So we can use proportional reasoning. So we know that 20 out of 50 had tags. We know at the beginning there was 1,000 that had been tagged out of some population. Well, the proportions should be equal, which means you can solve it like a proportion. In other words, we can cross multiply and solve. So 20 times n, 50 times 1,000, and n is 2,500. Okay, hypergeometric things, repeated dependent trials aren't anything new. It's just something we've done before without the name. Okay, some questions to try. Okay, give these ones a try. Tomorrow we're going to mix all the different types together. So we'll have uniform, binomial, hypergeometric. We have to try and tell them apart and how to remember how to actually solve these ones.